our midterm this week. The specific time of the midterm, because I put it in online, so it's not a in-person test, it's an online test. So I plan to do this way. In our Wednesday's class, I will do review for midterm, review class. So I talk about explain questions in 3 quizzes and homework assignment number 1. Yeah, all the problems, so I explain in our Wednesday's class. Yeah. Then I set up midterm tests, part A, part B. Yeah. Part A, part B, 2 assignments. Part A in the quiz format. Quiz format, the starting time is right after our class at 8 o'clock. So after we complete our Wednesday's class at 8 o'clock, that's the starting time of the part A of midterm. Yeah. Also part B, yeah, I set both assignments, the starting point, right after our class time. Yeah. Then the deadline is Saturday. Okay, so you have remaining of the Wednesday, Thursday, Friday, the end of Saturday. Yeah, deadline, the end of Saturday. So you should have plenty of time for both part A, part B, 2 parts, the deadline. So that's the midterm. Yeah. All right, so if you have any other questions, just let me know. Okay, yeah. So then on Wednesday, I will talk about, the content part. All right, yeah, today, first, let's complete C.2. Then we try to complete part D. Then we finish module 3. Yeah. So after the midterm, we will start module 4. Yeah, we have module 4 and module 5. Module 5 pretty short. Yeah. So module 4 still it's an important, relatively long module. So we need to use the 3 classes to do module 4. Yeah. So then 2 classes for module 5. And containing review for the final. Yeah, we need to do review for final a little bit. Yeah. So actually 1 plus half an hour for module 5, and then the remaining time. Yeah. Remaining time for the review for the final. Yeah. All right. So that's the plan for the remaining of the semester. Okay. Part C, Fibonacci numbers. Yeah. So here, sorry, yeah, actually part C, right, yeah. The problem, we have seen the problem, Fibonacci numbers, but the question, how do we, so when we calculate Fibonacci numbers, there are 2 ways. The first way, programming way. So remember we have an algorithm. So here mainly I want to talk about the dynamic programming one, because that one is very valuable. So from the algorithm point of view, we have the dynamic programming solution, calculating Fibonacci numbers. But here we want to move to another way to calculate, mathematical formula. Mathematical formula, and when I develop the formula, so I want to talk about some problem solving thinking. Because we want to learn the problem solving thinking methods, ideas. All right. C.2, golden ratio. Yeah. So I think all of you heard of this concept, very famous concept, golden ratio. Yeah. All right. The question, why? Because our goal, we want to find Fibonacci numbers. Why these two concepts are correlated, right? Yeah, so here we want to understand that part first. So let's look at the golden ratio concept first. Yeah. So the golden ratio, so first we need to know the definition and its properties. Here, the picture here, so this diagram give us the definition idea. Yeah. So later I will explain how to use the line segments. Here you can see you have a longer line segment, you have shorter line segment, then you put them together, you have, A plus B line segment. Yeah. These three line segments, we can use some way to, make them correlated in the form related to the golden ratio. Yeah. So here you can see the formula already here. Yeah. Yeah. But later I will explain more details. Yeah. And the picture here actually gives you some nice properties related to the Fibonacci numbers. Fibonacci numbers. And at the same time, you can get idea of the golden ratio here. Yeah. First, from the numbers, you see some small numbers. 1, 2, 2, 3, 5, 8. You can see these are the Fibonacci numbers. The first few Fibonacci numbers. Yeah. So you make small squares. The squares with sizes corresponding to consecutive Fibonacci numbers. Yeah, you skip the 0, nothing. After the 0 one, so the first one you use side 1, the F1, Fibonacci number F1 as the side of the first square. Yeah. 1, F2, another one, right? So 1 you see twice because F1, F2 both have side 1. So that's why. So you put these two squares and align them, in some nice form. Then the next one, F3 equals, the size is 2. Then you can, align with first two squares, so you get a rectangle. Then the next one, F4, with the size 3, it can also be aligned with previous 3 squares. So in this way, you can see all the squares created with the sizes of the consecutive Fibonacci numbers, they can be aligned in a perfect way. Okay? Yeah. And another thing is, after you arrange in that way, you can draw quarter arc. So this side, quarter arc, okay, in this way, quarter arc, okay. Then you connect all the quarter arcs in this way, so you get a also nice curve, some nice spiral curve. Yeah. And some people related to the painting, yeah, because some people argue, if you do the painting following the relationship corresponding to these Fibonacci numbers, then the painting looks beautiful. Some arguments like that. Yeah. And another thing is because this spiral at the end, you can see there is a point, convergent point, right? Yeah, but because if you go along this curve, then the point, the end point, the end point actually, there is a limit of that point. Yeah, the limit of that point. And that limit point gives you, some ratio, golden ratio relationship. Okay? Yeah. So here you can see, the limit. Yeah. So limit somewhere here. Then you consider the ratio, because of this line segment, right? So then shorter line segment, longer. So then the ratio, some golden ratio. Yeah. So this kind of, interesting property. Yeah. All right. So now let us do the calculation. Yeah. Let's calculate the golden ratio, the first step. We start from the definition. Longer line segment, we use A. The length, before the calculation, we do not have idea. So how long it is. Yeah. The length of A line segment and the B line segment, both unknown. Yeah. 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 But we arrange, so actually, some ancient Greek people, so, some people argue. Yeah. So what is the most natural number you can imagine? Yeah. So they try to make a story to describe some natural, beautiful number. Yeah. So they make the story like this. Yeah. So when you align two line segments in this way, yeah, then you consider the ratio. Yeah. So these AB line segments should have the relationship like this. Yeah. The first ratio, A over B, the length of longer line segment over shorter, A over B, it's a ratio. Yeah. This ratio should be equal to another ratio. Yeah. The sum of the two line segments, A plus B, over the length of the longer line segment. Yeah. Yeah. And, those people, so they set this relationship and they want to argue the ratio derived in this way, yeah, some, nice, interesting way, yeah, then they feel that's the most beautiful number, most natural number in the world. Okay? So that's their argument, all right? Yeah. So here we want to calculate this ratio. Yeah. How large is this ratio? Yeah. All right. To do the calculation, yeah, here we only have one equation. One equation, okay? But we have two unknowns. A, B, two unknowns. So then you based on your equation knowledge, so when you have two unknowns, you need at least two equations to solve it, right? So one equation is not enough. Yeah. But here, actually, our goal, we don't want to find the length of A and B. We want to find the ratio of A over B. That's different. The ratio. So the ratio could be determined. Although A could be longer, shorter, B, you can stretch longer, shorter, but the ratio must be the same. Yeah. So based on that understanding, so we have a chance to find the ratio from this one equation. Yeah. To do that, then we do some transformation. The right-hand side, we can simplify it as 1 plus B over A. Yeah. After that, then we introduce one variable to represent the ratio, because we're only interested in the ratio. Yeah. Yeah. So let us introduce variable X to represent this ratio. Yeah. All right. A over B equals X. Then the right-hand side, B over A, it is reciprocal, 1 over X. In this way, so the both sides, we can use X to represent all the terms. So then we get the equation with one variable about X, this equation. Yeah. All right. Then after we simplify this equation, we get a quadratic equation. X squared equals X plus 1. Quadratic equation. Yeah. All right. Next, let us find the solution of this quadratic equation. Yeah. Quadratic formula. Yeah. Here, yeah. Let me just recall the quadratic formula. Yeah. When we solve this standard quadratic equation, yeah, we assume a cannot be 0. Yeah. Otherwise, it's not a real quadratic equation. Yeah. So we want to solve real quadratic equation. Yeah. So the formula is there are two possible solutions. Yeah. Negative b plus minus. Plus solution 1 minus solution 2. Yeah. Root of b squared minus 4ac. Then the whole thing over 2a. Yeah. This formula. Yeah. Now, let us apply this formula to our current quadratic equation. Yeah. A is 1, B negative 1, C also negative 1. So let us plug into the formula. Yeah. So we get x equals 1 plus minus 2 possible solutions. Yeah. Then root 5. Yeah. B squared minus 4ac, 1 plus 4, it's root 5. Yeah. Then denominator 2. Yeah. So here there are two possible solutions. Yeah. But the question is, the second solution, 1 minus negative 5 over 2, the numerator is less than 0 because 1 is less than root 5. Then the x, our second solution, is a negative value. Yeah. But if you go back to our original question, we set x as the ratio of a over b. How can x be a negative value? It cannot be ratio. How can you make a ratio negative value? Right? Yeah. So for that reason, yeah, we should draw the negative solution. Yeah. Yeah. If we want to, because our goal is finding the ratio. The ratio cannot be negative value, so we can drop it. So we only take the positive value as the ratio. Yeah. Yeah. All right. So now this positive solution, yeah, so people call it golden ratio. Okay? So approximately equal to this one, but here, because this number, root 5 here, this number is an irrational number. Not a rational number, irrational number. Yeah. So that means if you use the decimal representation, you have infinitely many digits. Infinitely many digits. But another problem is in these infinitely many digits, you cannot find any cycle. Yeah. You know, repeated cycles you cannot find. Yeah. So that's the probability of the irrational number. If you can find repeated cycles, then they are rational numbers. Rational numbers, repeated cycles. Yeah, you know, for example, 1/3. This, you know, this 3 repeated forever. Okay, yeah, and 1/7, right? Yeah. Yeah, 6 digit, as I remember. So this is one cycle, all right? Then next, this cycle repeat. You know, and infinitely many repeated cycles after that. So then, because they are rational numbers. Yeah. For irrational numbers, you don't have that property. Okay? So yeah. So that's the, you know, main difference. Yeah. All right. So this golden ratio, yeah. So we like to use a special Greek alphabet. Phi represent this golden ratio. Yeah. Yeah. Similar to pi. Yeah. So we use pi represent some special constant. Here, this golden ratio, this phi, we represent another special well-known special constant. Yeah. All right. Now, we need to consider the Fibonacci formula. Yeah. So this formula, so here I call it the magic formula because when you see this formula, yeah, f sub n, Fibonacci numbers, yeah, the nth, or Fibonacci number corresponding to input number n. Yeah. You get the exact formula in this way. Yeah. 1 over root 5 times big parenthesis. Inside the big parenthesis, the first term, phi to the nth power. Phi to the nth. Yeah. The second one, negative 1 over nth over phi to the nth. Yeah. So here, so what? Because at the beginning, it is not easy to understand why we can connect Fibonacci numbers to the formula here. We know Fibonacci numbers, they're all integers. Yeah. But the right-hand side expressions, you have root 5, yeah, reciprocal of root 5. So that will make the whole expression hard to get integers. Yeah. But inside parentheses, you use a rational number phi, and you raise phi to nth power, hard to control, right? Very hard to control. Then you modify minus, a reciprocal something. It is very hard to predict what are those numbers. Yeah. Yeah. But those numbers happen to be the Fibonacci numbers. Okay? A lot of cancellation. Yeah? It's a lot of cancellation. Yeah? So you have cancellation here. Yeah. The first round cancellation inside parenthesis. Okay? Then the second round division type cancellation. Then suddenly you get integers. Yeah. So that's why it's not easy to understand, to see why this could happen. Yeah. So, all right. We will find the reason. So we will discover. So why we can find the Fibonacci numbers in this formula. Yeah. All right. To show this formula is correct. Yeah. So the first thing we need to show the formula is correct. Okay. Yeah. Yeah. To show it is correct, yeah, we have two basic ways to show it's correct. The first way, because it is given, right? Someone gives this formula to us, so we can take some easier way to show. The easier way is you only need to verify it. Okay? You only need to verify some given formula. It's much easier than you discover some unknown formula, right? Yeah. So we take the easier approach first. We just verify it. Yeah. That's the first way. But the second way, because when we're not satisfied with this verification way. Why? If nobody gives you this formula, how do you know this formula? Right? In the real world situations, most of the time, you need to find the answers. Because most of the time, nobody will give you any answer, right? Yeah. So you need to discover unknown answers in the real world most of the times. Yeah. But remember, here I want to make connection to our old strategy. We make a guess and a verify. Although unknown, but if we have a lot of information, we can guess the answer first. Because after you guess, you can do verification. Yeah. That's why you can see the guess way also very important. Yeah. But here you can see the guess way won't work. Why? The form is so complicated. How can anyone make a guess like that, right? Yeah, it's impossible. Nobody can make this, unnatural. on natural gas, right? Yeah. So the gas way won't work. Yeah. Then we have to find a systematic way to find a solution. Systematic way. Yeah. All right. So that's the our Part D topic. Yeah. All right. Yeah. So here, after this, yeah, the next thing is, yeah. So I described what we are going to do next. So we will do in Part D. So we finish this Part C. Yeah. Yeah. This last topic we just introduced this golden ratio number. Yeah. But the remaining work we need to do it in our Part D. Yeah. Yeah. All right. So let me switch to Part D. Yeah. Part D we will focus on problem solving. Yeah. All right. Okay, all right. Problem solving. Strategies, techniques. Yeah, all right. All right, yeah. The title, yeah. 2 topics in Part D. First topic, Fibonacci formula. The second one, linear recurrence relations. Yeah. So these 2 topics correspond to 2 solutions. Yeah. The first, Fibonacci formula topic, we need to do verification. Yeah. Because we're given the formula, we only need to do verification. Yeah. The second method, we assume the formula is unknown, so we need to discover, we need to calculate it. So then we need to apply a problem-solving thinking and a strategy techniques to find a solution. Yeah. All right. Yeah. So I hope we can complete today. Yeah. Yeah. So, all right. D.1, verify Fibonacci formula. When we do verifications, remember last time. So here I recall what we did. Something related to this topic before. Remember, here I recall binary bit problem. Yeah, remember? Yeah. So here, recall our binary bit problem. All right. In that problem, we skip one verification step. Remember? So at the end, we write a formula. Yeah. So here, let me just write. Yeah. A function equals 1 plus flow function of. Yeah. So this formula, and we have the recurrence relation. Yeah. So we have the recurrence relation like this. As I remember, A of n equals A of flow function of n over 2 plus 1. Okay, all right. Initial condition. Okay, all right. Yeah. At that time, we need to do verification. Yeah. There is that. Yeah. But I said, yeah, I want to skip that verification. Yeah, because in this Fibonacci formula, we need to do verification another time. So I combine. Yeah. So I want to save some time. Yeah. 20 to 30 minutes. Yeah. That much time. So I only want to show you how to apply mathematical induction to do the verification. Yeah, mathematical induction. Here, let's review. Yeah, yeah. This is a topic of your discrete math topic. Yeah. All right. Yeah. All right. So this applying mathematical on this one, so I skip it. All right. So I only apply mathematical induction on the Fibonacci formula. Okay, all right. So when we do it, based on the mathematical induction, first we need to verify the special cases. The special cases we treat as the base cases. Because for the mathematical induction, you need to do verification for enough many base cases. So how many enough? So in this one, remember our Fibonacci formula f sub n equals f sub n minus 1 plus f sub n minus 2. This one, I call it a second order, right? Second order recurrence relation. Second order recurrence relation. Okay? All right. You know, the reason is the difference between n and the smallest subscript n minus 2, the difference is 2. So second order. Second order, that means you need to verify two base cases. F sub 0, the first base case is f sub 1, second base cases. Enough. Enough many. All right. Then after base cases verification, then you need to make induction assumption. All right. Then the last step is the main step. Main step. So verify a critical step. So here I delay the details. So when I go to the verification part, then I talk about. So then do the critical step. So the critical step, we need to, apply some special formulas. So, all right. So now, let me show you that idea. Our goal, we want to verify Fibonacci numbers generated by the original recurrence relation can be represented in this formula. That's our goal. All right. All right. How to verify this formula rigorously? So this mathematical induction, it is a rigorous way to show if a given formula is correct or not. Very powerful. All right. So for the verification step, base case, our first base case verification, plug in. When n equals 0, you plug into the formula, because 1, right? 1 over this also 1. 1 over 1 also 1. 1 minus 1, 0. Then it is 0. So the first base case is verified easily. Second base case, you plug in 1. Now you need to, apply the specific formula for the phi. All right. Then when you calculate, so here we need to do a little algebra here. All right. So in algebra, when we need to work on the expression like this, the second fraction, the denominator relatively complicated. So we want to make denominator as easy as possible. Because we have the experience. We know the numbers at denominators relatively hard to handle. Numbers at the numerator relatively easier to handle because we can split. Numbers at the denominator we cannot split. So that experience. So we want to do conversion, do the transformation. The transformation we want to do is, all right, we multiply reciprocal, okay? Not reciprocal, conjugate, okay? root 5 plus 1, its corresponding conjugate. Yeah. Root 5 minus 1. Yeah. It's conjugate idea. Okay? So here we use that formula. A squared minus B squared equals A minus B, A plus B. Okay? Yeah. Yeah. All right. So here, 2 not A plus B, A minus B, then equals A squared minus B squared. Okay? Yeah. So root 5 squared minus 1 squared, 4. Right? So the numerator becomes 4. Then 2 and 4, after cancellation, we get a root 5 minus 1 over 2. Yeah. After that transformation, you can see they have these two fractions. They have the same denominator, and the numerator, you can see minus 1, plus 1 cancellation, and the root 5, 2 root 5, 2 root 5, that 2 and the denominator 2 can be cancelled out. Root 5 and this root 5 can be cancelled out. So you get the answer is 1. The answer you get here is 1. Yeah? So it is also verified. Okay? It's correct. Yeah. But here you can see the verification a little harder, right? Yeah. So when you get a larger and larger input number, the verification becomes harder and harder. Yeah. Based on the mathematical induction, it's already enough. Yeah? Yeah. Because we only need to verify 2 base cases. That's enough. Yeah. But here, I want to do one more step. Actually, I want to do 2 more steps. My purpose is I want to show you some algebraic techniques, also related to problem solving, but regarding this question here, mainly I want to show you some special algebraic techniques here to do the verification. Yeah. So let's do one more. This time, when n equals 2, yeah, here I do not apply that fancy technique, interesting technique. Yeah. So here I still use the, straightforward way, like a brute force method. No special technique, brute force way. Yeah. All right. Yeah, but here our second 1 over phi squared, because we already did transformation before, so we can borrow our previous transformation results here. Okay, so we only need to calculate the difference. Yeah, so that's not too bad. So we can do expansion. Yeah, we can apply the formula, a plus b squared, a minus b. We can apply the formula to do expansions. Yeah, all right. But after we expand them, you can see this 5 and the 5 cancel out. 1 and a 1 cancel out because negative sign here. All right. 2 root 5 minus negative 2 root 5, you have 4 root 5, right? Yeah. 4 root 5, 4 and 4 cancel out. Root 5 cancel out. So your answer is 1. Yeah. All cancel out. Okay. So then the answer is 1. Yeah. And we know f sub 2 equals 1. Yeah. So we verify this case. Yeah. Although for mathematical induction, we don't need this step. Yeah. But here we just practice some our algebraic calculation skills. Yeah. But the next one, I do one more. Next one, the calculation like this becomes harder, but I want to show you how to apply the properties of golden ratios. Yeah. The reason, there is a good reason, yeah, because later I will give you several questions in your quizzes, homework assignment number 2, and also midterm. You may have several questions related to the golden ratio using the properties of golden ratio. So I need to help you understand the properties of golden ratios better. Then you can answer those questions well. Okay? Yeah. Here, let me show you how to apply the properties of golden ratio in our number 4 verification, F sub 3. Yeah. All right, now we need to calculate this one. But if we use the brute force method, then too much work. Yeah. Although we can do, so use the similar way in our verification number 3. We can do it, but here we want to use a smart way. So not that kind of brute force, hard work, the messy way. The smart way, we need to go back to our golden ratio, the original equation for the quadratic equation for the golden ratio. So here, let's recall. All right. And here, what do we want to do? Because the reason the calculation relatively hard, because the degree of this phi cube is relatively high. Okay? Yeah. The higher the degree, the harder the calculation. So how to make it easier, make our calculation easier? The idea, reduce the degree of phi to the third. But question, how to reduce the degree? By the properties of golden ratio. Golden ratio has some properties. So we need to go to the golden ratio properties. All right. There are 2 golden ratio properties. All right. These 2. Look, how do you know golden ratio should satisfy these 2 equalities? It's very simple. Remember, how do we find the golden ratio? Okay? We need to recall, how do we find the golden ratio? By solving quadratic equation, right? So this is quadratic equation. So golden ratio must be a solution of this quadratic equation. Then when you plug in, the golden ratio should satisfy this equation, right? So you just plug it into this quadratic equation. It must be, equality, right? Equality. Then, can you convert this equality to the first one and the second one? You just write in 2 different ways, right? So you use the basic algebraic manipulations, move terms from left to right, from right to left. Then you can easily get these 2 terms. The first property, you move this, or you plus 1 both sides, right? So you get 1 equals phi squared minus phi. The second one, because sometimes you need to work on phi squares, so you move these 2 terms to the right-hand side, so you have phi plus 1. Based on your situations, you can choose one of the 2 properties to help you do the transformations. All right, here, let me show you how to bring down the degree of phi cube by using these 2 properties. All right, so here I already explained how to get that. All right, so let's work on phi cube here. Phi cube, now we can break it into the product of phi times phi squared. Because we want to reveal that phi squared. Make it stand out. Then we can replace it by another expression, phi plus 1. Okay, all right. Phi plus 1, phi times parenthesis phi plus 1. Okay, all right. So then, multiply through, we have 2 terms. First term phi squared plus second term phi. But the first term phi squared, can we apply this second property another time? You can replace phi squared by phi plus 1, then you bring down the degree another 1. Okay? Yeah. Even lower. So after the simple simplification, you have 2 phi plus 1. Yeah? The degree much lower, so much easier to handle than degree 3 expression. Yeah. All right, so that's the first one. The second one, we also need to, this time we need to bring down the degree of denominator. Yeah. Denominator a little harder than the numerator. Yeah. Yeah. All right. Now, so let's do denominator. In order to make the degree of denominator lower, so we imagine some common way people use to make the degree of denominator lower. Cancellation of common factor. If your numerator denominator have common factor, you can do cancellation. After cancellation, you bring down the degree of denominator. That idea. Okay? Yeah. So based on that understanding, yeah, now we need to try to make common factor. Yeah. All right. So here, because 1, usually when people see 1, because 1 is the simplest number already, right? Yeah. How can you make 1 even simpler? Yeah. It's hard. 1 already the simplest number. Yeah. But here, sometimes you may need to go to the opposite direction. You do not want to make the form the simplest form. You can make the form more complicated. Yeah? So you go the opposite way. You do not go the simplification way. You go the reverse way of the simplification. Yeah. So here, we replace 1 by, based on the first property, it looks more complicated, but the good thing is after this substitution, you can see common factor between numerator denominator. They can do cancellation. Yeah. Because we want to do cancellation. Yeah. Our goal, we want to make the denominator as simple as possible, but we allow to make the numerator a little more complicated. Yeah. Because you need to sacrifice a little bit, right? Trade-off. You make the denominator simpler, but as a trade-off, you need to make the numerator a little harder. Yeah. All right. After cancellation, we have this numerator phi minus 1. Yeah. Denominator phi squared. Yeah. Simpler than before, but not enough. Okay. Yeah. Because you see another 1 here. When we see 1, you can connect to the first property of golden ratio. Yeah. This time you can replace that 1 by another round phi squared minus phi. Yeah. Because after simplification, then they have common factor another time. Okay? Yeah. Common factor. All right. This time after simplification, you have 2 over phi minus 1. Yeah. Now it looks pretty simple. Yeah, pretty simple. All right. Now we think we are ready to do the calculation. Yeah. Because these two forms, I think we are ready to do the calculation. Yeah. Let us add these two expressions together. Yeah. So after you factor 2 out, you have phi plus 1 over phi. Yeah. And these two forms, now you have this equality. Yeah. Can you? Yeah, because if you multiply 1 over root 5, both sides, what do you get? Based on the formula here, 1 over root 5. So what you get is F3 equals 2 times F1. After you multiply 1 over root 5, both sides, the right-hand side is 2 times root 5. The left-hand side is F3, 2 times F1. F1. Left-hand side, F3. So you get this. That means because F1 equals 1, that means F3 equals 2. Yeah. Yeah. So so you verify the case number 4. Yeah. And here, the method I show you, we apply the 2 properties of golden ratio. Yeah. So you have the experience. Yeah. Later, when you see some polynomials, yeah. So you see a polynomial of golden ratio, yeah. So you can use these 2 properties, yeah, to bring down the degree of your top polynomial. You can always bring down the degree of polynomial. Think about that. Okay? All right. Yeah. So after that, yeah, so we pass the base case verification step. Yeah. Next, we need to go to the general case verification. The general case, we need to apply, yeah, so 2 steps we need to do. First step, make mathematical induction. Make that induction. Yeah. Write a statement. Write the, second step, make that assumption. Make the assumption of induction assumption. So we call it induction assumption. We make that. Yeah. So the statement. Yeah. Yeah. So the step 2, just the statement. All right. Yeah. But step 3, we need to do the general case verification. Yeah. Yeah. Based on that statement. Yeah. Based on that statement. Yeah. Here I need to explain. Yeah. So when I show you this verification details here, I need to explain the logic. Why, if we do the mathematical induction here, we can prove the formula is always true, always correct. So what's that logic? Yeah. All right, D.2. All right. Now we need to do the main part of the work, the proof, the hard part. Yeah. All right. Here we use the powerful tool mathematical induction. Yeah. All right. Yeah. The base case is we did it. Yeah. Step 2, we need to make induction assumption. We need to assume, make that statement, assumption statement. Then we need to apply this assumption statement to do the general case verification. All right. So what statement do we use here? Yeah. All right. Assume that a formula is true for certain range. So this is the certain range. Yeah. Certain range, actually, we for this lower end, we can extend to 0 and 1. Okay? Yeah. Because the range we can contain 0. Because 0, we already prove it. We know it's true. Yeah. Yeah. So you can include 0, 1 in the range. Yeah. All right. Yeah. All right. Then the upper bound is some, yeah, so actually, yeah, let me write in a more clear way. Yeah. So here, because this range, the range is critical here. All right, so let me write clearly this range. All right. 0 less than or equal to k less than or equal to n. Okay, all right. Yeah. With n greater or equal to 1. Okay, yeah. So the clear way is, yeah, no, all right. Because this is the range. Yeah. So we assume the formula is true. What do you mean formula is true? The formula is true. Do I write it below? Yeah. Yeah. So this is formula is true when k falls into this range. It's true. That's assumption. Okay, that's assumption. All right. We assume it's true. Okay, all right. Yeah. And when n equals 1, we already answered, right? N is 1. The base cases tell us this range, this statement is true when n equals 1. Yeah, all right. But how do you know this assumption is still true for n equals 2? True or not? Right? Yeah. Yeah. How do you know n for any positive integer is true? Because our goal, we want to show for n equals any positive integer, this assumption is true. That's our goal. Okay? But we need to rigorously prove it. We must rigorously prove it. That's the point. Okay? That's the point. Yeah. All right. So So in our pocket, we have something. Yeah. Yeah. So when you, here, let me convey my problem-solving thinking idea here. Yeah. All right. When we want to do something, we have to have something in our background to start with. If we have nothing in our background, then we can do nothing, right? Yeah, because, you cannot grow. You have nothing to grow, okay? But even if we have little tiny thing in our background, we can grow it. We can make it, add to our experience, grow more and more our experience when you have something. Here we have something. We have something in our pocket. So we can grow that. So what's in our pocket? Yeah. Because this range we know when k, so here, this k is in this range, we know the statement is correct, right? Yeah. So that's our base case. That's our base case. All right. Now we want to grow from our base case. Yeah. Base case too small. We want to grow it. Okay? Grow it. Make the range larger and larger, and at the end, our range covers all the positive integers. How about that idea? Okay? Yeah. We grow it. So here we use the growing idea. Yeah. So how to grow? All right. How to grow? Yeah. The first time, can we grow this range to a larger range the first time? Yep. Yeah. So we keep our goal very modest, okay? Not very aggressive. Only move one step forward, okay? The modest step, one step forward. Growing from upper bound 1 to upper bound 2. Yeah. Yeah. All right. After we do that, second step, can we grow from this range to another larger range? Right? If we make it, yeah. Next, can we grow from another higher, larger range? Right? Yeah. Yeah. But if we take this idea, yeah, we don't want to repeat similar work again, because when you do the work here, quite similar, right? Yeah. The work quite similar. Yeah. So we don't want to repeat the similar work again and again. Do we have some efficient way to do the similar work? Here we want to look for some efficient way to do the similar work. Or can we work on a general growing step? This general growing step can cover all the possible growing steps. How about that? Here, our goal, we only want to do one growing step, but this growing step is so general. Okay, so general. This general growing step, we can apply this general growing step on all the cases, all the similar cases. That's the idea. Before, let me use a few minutes before the break time to describe this idea. This idea, very important. Why mathematical inductions can show some statement is correct for all the integer numbers. That's the power. So here, I explain the critical point here. All right. Now, I talk about the general growing step. Okay, how general? Okay, all right. The general is like this. Suppose currently we show this induction assumption is true for k in this range. Yeah. Here I do not use specific number. I use some n number. Yeah. It's true for certain n number. Okay, all right. Then I just do one growing step proof. Yeah. The proof, only do one step. It's enough. This step is, then I can show, the statement. True for a larger range, k in 0 n plus 1. I grow the range by 1. But this is so general. If I can prove this general step, then can I apply this general step for n equals 1 first, n equals 2? I can apply the same thing. Because I did it rigorously, right? If I do it rigorously, after that, I enjoy the result of this result, right? I enjoy it. Okay? So I apply it to n equals 2, n equals 3, n equals 4, n equals 100, 1 million. Can I grow to make the upper bound infinite many large, right? Yeah. Then we cover all the integers, right? Yeah. That's the essence of this mathematical induction idea. Yeah. We do not do too much work because we only need to do the general work. Yeah. General step proving. That's it, enough. Okay? Yeah. So try to understand in this way. Then you agree, it's a rigorous proof. Yeah. So there is no hole there. Okay. Yeah. All right. Yeah. So next, we need to implement this idea. Yeah. So here, let me give you the statement. Yeah. Yeah. Then we take a break. After the break, so then I show you the, implementation details. Yeah. So then we've completed this formula. Then we do the, next main topic is the recurrence relation topic. Yeah. All right. So now our goal, step 3, we need to verify. Yeah. Look at here. We show this formula is correct, but this time you can see the subscript becomes n plus 1. n plus 1, it corresponds to, so we enlarge the range, right? Yeah. Because in the range, your assumption, your statement is only correct when the upper bound, k, the largest possible k is n. Yeah. It's not, you cannot apply it directly for largest k to be n plus 1. You cannot apply, right? Not allowed. But here we do not apply that statement. Here we use this original recurrence relation. We show this must be correct. after we show this is correct, then we extend our original statement to be true in a larger range. That's the idea. Yeah. Yeah. So you can see. Yeah. All right. So that's the logic. All right. So let's take